Now we have Nadia from UCSD telling us about synthesis.
Hi, everyone. This is a preview for Synthesis 1. There are 2 synthesis sessions at this conference, which is very exciting. This one is today at 3:10 in Grand Ballroom A. Okay, what is this program synthesis thing? The idea is we want to be able, we don't want to write programs anymore. That's so like 2001, 8, whatever. So we want to just tell our computers at a very high level, provide some specification of what we want our program to do, and somehow automatically transform this into a program, right? And the idea is that the difference in levels of abstraction between the spec and the program is so large that we cannot usually just do it by deterministic transformation. Instead, we need to define some kind of search space, and then some search is involved. We will search in the space to find a program that matches the specification. And then, so the main challenge in program synthesis is usually that this program space that we want to search in is really big. Otherwise, we wouldn't be able to find many programs that the user actually wants, right? And so the search is hard, right? That's what most papers address. Okay, so let's get to the papers. The first paper in this session, we'll start at 3:10, is called Inductive Synthesis of Structurally Recursive Functional Programs from Non-Recursive Expressions. So I highlighted a couple of keywords here, inductive and recursive programs. So let me quickly say what that means. So inductive synthesis just means synthesis from examples. You will be giving input-output examples to your synthesizer as the specification. So for example, maybe you want to synthesize like list transformation, a very simple one. You want to synthesize the function to compute the length of the list, right? So you could give it examples like, well, empty list goes to 0, list 1, 2 goes to 2, right? And then you might give it some components that the synthesizer might use in the program. So you might say you can use number 0, 1, you can use plus, and you can use the list constructors, right? And then the synthesizer might come up with a recursive program like this, which is like a regular program for computing the length of the list, right? All right, so typically, so I said that there's the search involved, right? And there's a lot of programs to search through. And so many synthesizers in this area, they sort of use this technique of, they generate hypotheses about what the program looks like, and then they try to reject them early before filling in all the details. So for example, we might say, if this is our hypothesis, we know that's not correct because this one is returning 1 for an empty list, and we know we need to return 0 for an empty list. So even without filling in this part of the program, we can reject it, right? However, the challenge with recursive programs is that if you have a recursive call in your hypothesis, because you don't yet know what it's doing, because you haven't synthesized the program yet, it's hard to reject them because you don't know what they're doing, right? And this is kind of the challenge that this paper is addressing. And the inside of this paper is, well, if you only look at your problem for each one example individually, you never need recursion to solve that. You can always solve that using a straight line program, right? So what this paper is suggesting is that you have a 2-step process, and in step 1, you're just trying to solve each example individually, and to do that, you're basically just generating a whole bunch of simple expressions that solve each example individually. So, for example, for this one example, what kind of expressions can we make from these components? Well, we can say 1 plus 1, right? Because we just need to return 2. That's all we care about, right? So it can be 1 plus 1. It can be this, that. We generated a bunch of possibilities, right? Then step 2, once we have a hypothesis, which is a recursive hypothesis, right, that we want to check if it's feasible, if we should throw it out or we should keep it, right, if it's hopeless. What we can do is we can kind of try to see if it matches any of these things here, right, on this particular example, right? And to do that, we kind of like symbolically execute or unfold this hypothesis, right? So here we're like, oh, okay, our input is 1, 2, so we're going to take the second branch of the match, right? So we kind of get this expression that has itself a recursive call. Here we again take the second branch. Now we take the first branch. So we kind of like unfolded it to this expression here that still has some holes in it. And now we see, does that match anything here? And yes, it does, right? So we have the 0 plus 1 plus 1, which looks like that. So means that this hypothesis is fine. We should further explore it, should not throw it away. If it didn't match anything here, we can throw it away. Good? That's the first paper. Okay, second paper. Flash fill ++, scaling programming by example by cutting to the chase. So here the setup is again synthesis from examples, right? This is what programming by examples refers to. This in particular is more about string transformations, right? So how many of you have heard about flash fill? So it's this cool feature of Excel, right, that helps you fill in your spreadsheets, right? So you can give it examples like, oh, I want to extract the first name from my full name, and it will find some program and fill in the rest of your spreadsheet, right? So for this particular kind of simple string transformations, this is already solved by flash fill, right? But what this second paper is trying to address is, what if you want more sophisticated programs which have a lot more components? So not only the simple string transformations, but if you also want arithmetic, date operations, things like that in your programs. So for example, if you have this example here, what you might actually want to do is, extract a substring, after this dollar, but then also round it, right? So it has some arithmetic involved, right? And then this is harder because the search space is larger and whatnot, right? So this is kind of what this paper is trying to address. And the main insight in this paper is, let's let the language designer, the designer of the synthesizer, give us a bit more information to help the search, right? And the kind of information that they allow you to provide is what they call cuts, right? So I'll try to give a very high-level intuition. So for this particular example, let's assume that the synthesizer has a hypothesis of this form, right? Maybe we want to round something, right? So what the cut is going to allow you to do is going to say, well, the only two values that are relevant for this whole that can go in here are this 24.58 and this 46, because these are because the cut kind of knows that you need a number to go in there, and these are the only numbers that appear in the input, something like that. Okay, sounds good? Okay, 2 minutes for the last paper. Last paper at 4 p.m. is called Unrealizability Logic, finally a short title that I can actually pronounce. Okay, so what this paper, unlike the other two papers that focus on, let's find the program, right? There's also this important question is, when there's no solution, how can we prove that there is no solution in the search space that satisfies the specification, right? This is what unrealizability means. A synthesis problem is unrealizable when there's no solution in the search space. And so to understand where this fits in, how many of you have heard of Hoare logic? Okay, most people, right? So Hoare logic we can use to prove programs correct, right? And this is basically, the basis of most program verification research these days, right? The way Hoare logic works is it allows you to compute an over-approximation of all the reachable states of your program, right? And then you can look at all the bad states that you don't want, then you can prove that they don't intersect, and then the program's correct, right? So in this little while loop that I wrote on the right, we can say that x can only be even after this while loop, right? No matter how many times it iterates. But the bad state is that x is 11, and 11 is not even, so they don't intersect. Okay, program's correct. So the insight behind this paper is, let's do the same, but for synthesis. And what do I mean by that? Is, well, instead of a set of reachable states of one program, let's compute or over-approximate the states that are reachable by all programs in your program space. Then let's also look at the states that your spec wants you to end up in, right? And then if we can prove that these two don't intersect, then we can show that the synthesis problem is unrealizable. That's it.
The session is over, but if we have any questions, I guess we can take one. Yeah, one question.
Why care about internet?
Why do you care about it? I think the authors will address this, but there are a lot of applications actually. So one of the applications, if you want to do optimization, if you want to find the best program according to some cost metric, as part of that, you would need to prove that there is no program that's better than one you already found. So that's one use case, but there are actually many. We can take this offline.